in our research, we've actually looking at it more of a process level. So taking large models and breaking them into pieces. So we think it's valuable to, instead of taking overall SWOT, so I teach a hydrology class and we cover SWOT, and SWOT's a great model, but it's incredibly difficult to cover in a class because there's just so much going on. And so the students kind of get the view of it as a black box almost. You put information in, information comes out without a really good sense of what's happening on the inside. So we're taking models like SWOT and trying to break them apart into the individual components so they can kind of at least see how the data flows through the model and understand how different sub-processes within that model are operating on the data. So here's an example. So the Coweta watershed is an experimental watershed just over the border in North Carolina with long-term observational data. And so from within this Hydro desktop, a student or a researcher can go and pull up the information, can search for relevant time series within the HIS. Here you'll find some stream flow data at the outlet of this small little watershed here. We have some stream flow observation, and this point here is representing some climate information. And so it goes and fetches that data and downloads it to the database in a pretty easy fashion for the end user. And meaning they don't have to do a lot of the transformations themselves, so it's really a time saver. In the hydrology domain, this is how I like to think about modeling. This is from Keith Bevan, rainfall runoff modeling. So it's all the way back to thinking about what the processes are. What are the dominant processes within that watershed? Deciding what type of equations to use to represent those dominant processes. Getting the code to work properly. Do you have the right model parameters doing calibration and doing validation? And when I think about modeling, I want to be able to ask questions about each one of those steps. So I want to be able to quickly change out the processes if I think I have the wrong processes within the model, or I want to add a new process, so I want to have a very flexible system, and that's something that we're trying to build here with this hydromodeler application. And so as you can simulate it, you can flip back and forth between the graph and the map view, and you can quickly rearrange the components to try to test some other idea that you might have. You can package up this model, send it to a colleague, and try to have them run it as well. This is an OpenMI compliant environment too. So if you have an OpenMI compliant model, you can also drop it into this environment and it works. And that's at the end of the day, that's the advantage of the standardization is that a model that's created by some other organization can also drop into this environment. Or one of the processing models that an academic researcher builds could, in theory, go into some other OpenMI environment. So you have this kind of interplay between academia and other modelers. I put this slide in here because I think maybe some of you at least are thinking, well, isn't this a lot like EPA basins? If you're familiar with EPA basins. Is anyone familiar with EPA basins? Okay, a couple folks, all right. I think it is very similar. I think the target audience is different. I mean, we're... Okay, one's funded, one's not.
No.
Okay, maybe this is not relevant. But let's suppose that both were funded. I think they have similar goals, maybe different communities. We're both built off the same open source GIS system, and so there's some interplay between the two, and hopefully some transfer of knowledge across both of these activities. Let me just finish here with an example of something that we're doing in my group. So I do a lot of technology work. So but I am trained as a water resources engineer, and I'm actually interested in water resources questions as well. And so one of the questions one of my grad students is asking is, what is the impact of climate variability, not long-term climate change, but just changes within precip and temperature on a year-to-year basis? What impact does that have on nitrogen loading to streams? So if you can kind of isolate that change in temperature and precip between different years and kind of isolate that and control for that, and then see what's happening with nitrogen transport is the goal of this research. So he's using the Sparrow model that I think is coming up in a coming talk. So we'll address more detail the Sparrow model here. Essentially, it's a regression model, but it's spatially explicit. It has concepts of mass balance, so it's somewhere in between a mass balance model and a statistical model. And one of the difficulties with running this model is setting up the data for it. And just the observational data alone can be a hassle for researchers in particular that don't maybe have direct access to USGS information. And so using the quasi-HIS, what we did is created a script that essentially went off to the USGS and downloaded all the information we needed for stream flow and nitrogen concentrations, and then did some little processing routines to kind of combine those together to come up with a loading estimation. And I think that's important primarily because it's reproducible. We go to the direct data source and we pull the data, process it to create input for the model. And so if some other researcher wanted to say, well, I'm not sure you did that right, they can reproduce it. And that's something that's actually somewhat difficult to do right now, I think, in our community. Getting that whole data flow working in an automated way that can show reproducibility of results. And these are the results. This work is still it's in revision for water resources research. Essentially what we're seeing here is if you look at the overall map, let's see if I get my mouse working here. If you look at the overall map between these 2 years, 92 and 01, we use these two because we have good land cover data sets for those two. This is what the nitrogen loadings look like. If we look at just the impact from hydrology, so we hold nitrogen source change constant, we get a map that looks like this. If we hold hydrology, meaning climate, meaning temperature and precipitation constant, we get a map like this. So we identify certain hotspots. So these hotspots we think are due to changes in source contributions relative to changes in precip or temperature. So in a way, trying to attempt to control for hydrology changes. So in summary, I hope I've conveyed to you a little bit about the hydrologic information system that we are building and have built over the last couple of years. And it's really about finding new ways to access these large and growing data sets that we have and making them useful and easy to use for academic research. And one of the science challenges, I would say, more from an information science perspective, is how do you integrate this data across the multiple data providers that put out the information. And I think this really advances science and engineering in a number of ways, helping people find relevant information to test hypotheses and to do analysis, taking care of some of the tedious tasks that have to be done of merging data, and error-prone steps as well. I mean, grad students spend a lot of their time doing these steps, and as a PI, it's hard to really watch every single step that they do. So the more error-prone we can make those things, I think that's a really good progress for science. Automating the steps so they can be reproducible, and just making the whole workflow going from data to knowledge. The more we can automate that, the more we can reproduce results. I think it's good for science. So that's all I had to say, and I put my contact information up here. If you have additional questions, I'd be happy to answer them. And I don't know if we have time now. Sure.
Have you considered in this system including data sets that come from modeling information, such as hydrology, obviously precipitation, temperature important, and there's vast amounts of information that come out of models like WARF or MN5 or things of that nature, as opposed to just observational data. Have you thought about that as being part of your data source? Because I think that is an area that really needs to be checked.
Yes, that's a great question, great point. We focus on observational data early on because it's kind of the bread and butter for hydrology, A, and B, because of efforts from OGC and from the climate community with things like OpenDAP that are protocols for moving gridded information across the web. We felt like that space, if you will, had some progress in it, and that we could leverage some of those existing tools for geospatial data or model output data. The goal that we have now is to make Hydro Desktop able to tap into those resources instead of creating standards for those accessing that information. So at the end of the day, we can have kind of a central hub, that's going off and looking at different information. So you may be using our protocols for getting observational data, but using somebody else's protocols for getting climate data and weather data. So Yeah, obviously that information is very relevant and useful for hydrology, but I think we didn't focus on it primarily because there was other people working in that area.
With regard to the applications, could you kind of give us a sense how broad of a range of your applications, groundwater, unsaturated zone, estuaries, rivers, watersheds, what examples do you have if we go to the Kawasi website of this being demonstrated?
Okay, so I'll answer that by saying that the HIS is really about just data standards and data integration, and we're here to support the hydrologic science community. And hydraulic scientists are doing all kinds of stuff, and I'm sure you know. I mean, in these domains that you're talking about, and I think our goal is to make their work easier to do, make it better by having access to better information. We don't have examples on the website. We don't have a lot of examples of how it's being applied. And maybe that's something we should think about and include, as it's in academia, we write papers, and we hope that when people write papers, they acknowledge that they use our system. Maybe there's some way to look through that archive and say, okay, here's a collection of papers that. I mean, I know in my group we have 3 or 4 different projects that are being leveraged off of the HIS and this ability to pull the data quickly. I'm sure others do have examples as well, but we don't have a great collection of that information. That's probably something to consider. Yeah.
Thank you.
Oh, okay.
We're running a little bit behind. Annie, are you on the, are you there? Annie's supposed to be at 11:15, 11:10. I think this is 5 minutes. Yeah. We'll try and get Annie started no later than 11:20.
Restrooms are in the back. Tell them, and water fountain. Yes, I'll take up there, right?
Who's introducing Annie?
By the way, do you know Alan Gellis? That's who I was talking to. Maryland.
Are you introducing Annie?
We're missing the go-to-meeting gentleman at the moment, so we're going to proceed anyways and move to our next speaker. We have the speakers, I should say. We have their slides up on the board behind us. And since I'm short, elevationally challenged, I'm going to be pressing, I heard that, Annie. I'll be pressing the go button to move the slides forward. So, Annie, if you can, I'm sure you can hear me. Just say now or something. But let me introduce you first. I've had the pleasure and the honor of working on an organizing committee that Annie Jerbeck heads up. And this is on the Global to Genome program, and there's hopefully Annie will mention something about a workshop in May of 2012, which is relevant to all of the discussions and topics that have been discussed today and tomorrow. I'd like to introduce our 2 speakers, actually. Annie Jerbeck, Senior Toxicologist and Special Assistant to the Associate Director